Hey folks, let's talk about scaling infinite series. So we've learned previously that we need to take great care in extending finite operations to an infinite series. So naive attempts to apply commutativity and associativity across an infinite number of terms can lead to catastrophe. So we need to take pretty extra care in making sure that what we do is legitimate. And we wish to establish that factoring or distributing a constant across an infinite series is a completely legitimate operation. That is, k can be distributed across an infinite series, or if you read this in reverse, you can factor out a common constant k from an infinite series. So consider this series, the sum of k, a, n goes from 1 to infinity. And we're going to assume that k is not equal to 0 because that's a rather easy series to analyze by itself. That would be 0 plus 0 plus 0, etc. So the partial sum sequence looks like this. And here is a formula for the partial sum sigma n. And we can obviously factor out a k from this expression. There's absolutely no controversy here. The point being this is a finite sum, and so the distribution process and factoring process is completely legitimate. So now what we want to do is compare this to the unscaled version of our series, the sum of n runs from 1 to infinity. And here the partial sums look like this. So the sigma n is just k times Sn below. And now the limit as n goes to infinity of sigma n is going to be the limit of k Sn, and the k factors out. This is a standard limit law for sequences, and this is the key, this is the hinge. This limit law is the doorway to get the finite operation of factoring and scaling across finite terms to the whole series. So what we've found is that the limiting value of the partial sums of the scaled series is just a constant times the limiting value of the partial sums of the unscaled series. And so what that means is, since k is not equal to 0, if one of these limits converges, then so does the other. And if one of these limits diverges, then so does the other. So they sort of come together in their convergence property. And if one side has infinite divergence, then so does the other, with an obvious sign change if k is less than 0. So they both carry sort of implicitly the same information about infinite divergence in that case. And best of all, in the convergent case, the value of the scaled series is just what you would expect. So in other words, the sum of k a n is going to be k times the sum of a n. Everything works out just like you would hope. So this is a subtle but important point. Both of these expressions sure look like just equations. They're two things on each side of an equal sign. But the thing you have to remember is these things we've written down involve infinite series, which might converge or they might diverge. So you're not always talking about two numbers on both sides of the equation. But here's the cool thing. As implicit assertions about convergence, these equations, I would put air quotes in that case, are true. And better, in the convergent case, these are literally true as equations relating to numbers. So let's look at some examples. Here's example A. Fun fact, the alternating sum of the reciprocals of the odd numbers turns out to be pi over 4. You don't need to understand why this is true to appreciate this example. It is true, and it's something to look forward to as you continue your studies of infinite series. But here's what we're going to do. Given this fact, let's make a series that converges to pi on the nose. So what we'll do is we will take the original equation with a series on one side and pi over 4 on the other, and we will scale both sides by a factor of 4. And so on the right side, clearly we have pi, and on the left side, we now know it's legitimate to distribute this 4 across all the terms, and there we have this beautiful series that converges to pi. So example B, here's another fun fact. You may know this already, or you may be about to learn it, but the sum of the reciprocal integers, the so-called harmonic series, diverges to infinity. The sequence of partial sums actually races off to infinity. Well, I shouldn't say race off because it goes pretty slowly, but it is true that the limiting value of the partial sums is infinity. So what would be the fate of this series here, the sum of -3 over n as n goes from 1 to infinity? Well, there's this common factor of -3 from all the terms, and we've learned that we can legitimately scale that, or I should say factor that out. And because the sum of 1 over n diverges to infinity, that -3 is going to flip all the signs of the partial sums. And so what we were able to conclude is this series is going to diverge to -infinity. Okay, example C. Here's a series. What is its sum? Now, you may already have the theory down to understand this completely because you might recognize that this is a geometric sum. Its first term is 12, and the common ratio is a half, which, being strictly between -1 and 1, means this series converges, and it converges to the first term divided by 1 minus the common ratio. So you wind up with 24 for the sum of the series. But let's put that aside. Suppose you didn't know that. Well, what we could do is we could factor out the 12 and carefully see what the pattern is on the inside. And you might recognize this as being sort of the geometric series, 1 plus x squared plus x cubed, etc. This is the case where x equals a half. This converges, and if you only knew about that formula, then you would be able to say, hey, this is 12 times 1 over 1 minus 1/2, which of course is going to give you the same thing. So I offer this example not as a superior way of doing the problem, but just showing you that all the pieces fit together as they should. So in summary, if k is not equal to 0, then the equations/operations, which you see here, preserve convergence and are true statements, i.e. equations relating values of convergent sums, and they preserve infinite divergence with an obvious change of sign when k is less than 0. So you should feel free to go out and scale non-zero factors and distribute them fearlessly as you study infinite series.